Welcome to This Explainer. Okay, today we are going to dive into something seriously fascinating. The intriguing ways a seemingly lifeless hunk of metal and wires can actually interpret its surroundings. You know, we often look at robots and just assume they're these incredibly complex, totally alien systems. But what if their core mechanics aren't really alien at all? What if the blueprint for cutting-edge robotics is actually hiding right inside of us?
Picture this for a second. You're walking through a pitch-dark, obstacle-filled room with your eyes closed tight. What do? Well, you rely on your hands, outstretched to feel for walls, your ears listening for echoes, maybe even sensing temperature shifts on your skin, right? You use your natural senses to navigate safely. But it really begs the question, how on earth does a machine accomplish that exact same feat? How does a robot actually feel its way through the world when it doesn't even have a biological nervous system?
All right, let's dive right into this by grounding ourselves in the fundamentals. This is Section 1, How Bots Perceive.
So, the big takeaway here is that robotic perception, it isn't magic. It's simply how machines interpret their surroundings using artificial sensors. And here is the real secret. Those sensors directly parallel our biological senses. It's essentially a direct bionic mirror of our own biology, using carefully engineered hardware to understand the environment in the exact same way our brains use our bodies. It's pretty wild when you think about it.
To really wrap our heads around this bionic mirror concept, we're going to walk through Section 2, the Senses Showdown, where we compare the biological versus the artificial.
Let's start with human sight. Light floods into your eyes for your brain to process instantly, right? Well, a robot translates this mechanically. It wakes up and maps the world using camera lenses and simple light detectors. These artificial components capture the light and imagery, and they feed that data straight into a processor to create a digital understanding of what's around it. It is a literal direct translation of human sight into hardware. Moving on to touch. Obviously, a robot needs a way to register physical contact just like our nerve endings do. So it uses tactile bumper switches. When a robot hits a wall, that physical switch actually compresses, sending a super simple signal that just says, hey, contact has been made. It effectively replicates the biological sensation of touch using really basic mechanical hardware. And you know, this direct mapping just keeps going, right into our sense of hearing. Just as your eardrum vibrates to capture sound waves moving through the air, a robot uses microphones to pick up audio cues from its environment. This is exactly what allows the bot to process voice commands or react to loud noises in its vicinity. So, looking at this summary, when you map the artificial hardware one-to-one with our biological senses, the parallels become crystal clear. Sight translates to cameras and light detectors, touch maps right to bumper switches, hearing becomes microphones. Honestly, breaking it down like this really demystifies these complex robotic systems. Fundamentally, a robot is just using different tools to do exactly what human bodies have been doing for thousands of years.
But hey, bots aren't just limited to human senses. Which brings us to Section 3, the bat's ping, where we look at echolocation.
Imagine the high-pitched sound a bat makes while flying rapidly through a pitch-black cave. Ping! That sharp sound is a rapid sound wave. It travels through the air, bounces off the rocky cave walls, or maybe a tiny insect, and echoes right back to the bat's ears. This is exactly how the bat finds its prey and avoids crashing, all in total darkness.
So, taking a page right out of the bat's natural echolocation playbook, a robot uses ultrasonic sensors to emit high-frequency sound waves, and these are usually sounds that we can't even hear. Those sound waves bounce off an object and return back to the sensor. By calculating exactly how long it takes for that echo to come back, the robot can measure the exact distance to an obstacle. It's a total game changer. It allows the machine to effectively see its spatial environment without needing a single drop of light.
Okay, let's make all of these bionic blueprints super tangible with a role-playing activity in Section 4, the blindfolded bot. In this physical demonstration, students get to literally act out robotic perception. In Step 1, one student puts on a blindfold. They are the bot, entirely stripped of visual data. In Step 2, another student stands right beside them acting as the artificial sensor. As the blindfolded bot slowly walks forward, the sensor is watching the environment. Then, in Step 3, right before the blindfolded student hits a desk or a chair, the sensor taps them on the shoulder. That physical tap perfectly mimics how a bumper switch works in real time, instantly sending a signal to stop. It's just such an effective way to understand how simple inputs dictate robotic action. Ultimately, exploring these bionic blueprints strips away the intimidation factor of modern tech, doesn't it? It is simply hardware that successfully allows a machine to see, feel, and hear the environment around it. Whether it's a camera acting as an eye, a bumper switch acting as skin, or an ultrasonic sensor acting just like a bat in the night, robots are fundamentally just navigating the physical world using artificial reflections of the natural world.
So I want to leave you with this final thought to ponder after this explainer. If a robot's sensors mirror our own biology so perfectly, where exactly is the line between machinery and living reality? As these artificial sensors get more advanced, inching closer and closer to seamlessly replicating our own biological experiences, how is that going to change the way we relate to and interact with machines tomorrow? Thank you so much for hanging out with me to explore the mechanics of robotic perception. Keep questioning, keep learning, and I'll catch you in the next explainer.